Hi students, already we had discussed the two cryptographic methods. They are substitution techniques as well as transposition techniques. In last video we had discussed some of the substitution techniques like Caesar cipher, monoalphabetic cipher and Playfair cipher. Now we can study the other three substitution techniques. One is Hill cipher, second one polyalphabetic cipher, and third one time pad. Okay, so first one, Hill cipher. So it's a multi-letter cipher. Okay, Hill cipher is a multi-letter cipher. That means we can take more than one letters at a time and then convert it into ciphertext. That means we can take m successive plain text letters and then convert it into m ciphertext letter. For that, we are using a system that is a linear equation system. So we can take m linear equation systems to convert m successive plain text letters into m ciphertext letters. Okay. Here m is equal to 3, then the system can be described as follows. That is, C1 is equal to K11 P1 plus K12 P2 plus K13 P3 mod 26. Same way C2 and C3. Okay. Here we are using a linear equation system model in Hill cipher. Okay. Then what is P1, P2, P3 and C1, C2, C3? P1, P2, P3 are the three successive plain text letters. C1, C2, C3, it is the ciphertext of P1, P2, P3. Okay. Then what about K11, K12, etc.? It is a key 3 by 3 matrix. Okay, why we are using a 3 by 3 matrix here? Because we are using a 3 linear equation system. We are converting 3 plain text letters at a time. So that we can use key as 3 by 3 matrix. Clear? So the system can be described as follows. That is C1, C2, C3. It's a 3 by 1 matrix. It can be formed from a 3 by 3 matrix into 3 by 1 matrix mod 26. That means C is equal to KP mod 26. Then what about decryption? Decryption is the reverse process of encryption. That means in decryption, ciphertext is converted back into plain text. So P is equal to K inverse C mod 26. Okay, it is the inverse of key matrix into ciphertext mode 26 is the process that is taking place in decryption process. So this is about Hill cipher. Hill cipher is a multi-letter cipher mechanism in which a linear equation system is used. We can convert m successive plain text letters into m ciphertext letters. Clear? And consider an example here. We have a plain text, pay more money, and we choose an encryption key, K equal to a 3 by 3 matrix, 17, 17, 5, 21, 18, 21, 2, 2, 9. It's a 3 by 3 matrix. So m equal to 3 here. We can convert first 3 letters of plain text into ciphertext. Then next 3 letters into next 3 ciphertext and go on. Okay. So first 3 letters of the plain text are represented by using a vector or by using a matrix. So first 3 letters of the plain text is PAY, pay. Okay. So we can convert it into a 3 by 1 matrix. How? Every alphabet is assigned a number. From A to Z, we can assign numbers from 0 to 25. Okay. In PAY, second letter is A. A is the first letter. So which number is assigned? 0. So second row of the first matrix, that is 15, 0, 24. It is the number is 0, right? So 0 is the number assigned for A. Same for P, it is 15, and for Y it is 24. So we can construct a 3 by 1 matrix by using these numbers 15, 0, 24. Okay. So 15, 0, 24 into K. K is 17, 17, 5, 21, 18, 21, 2, 2, 9. It's a 3 by 3 matrix. Then it's a matrix multiplication, right? So KP. K matrix is multiplied with a P matrix. Then more 26. We will get 11, 13, 18. And the letter that is for 11, 13, 18 are L, N and S. So, Pay, P-A-Y can be converted into LNS. Likewise, we can continue for other plain text letters. Then we get a cipher text letters LNS, HTL, EWM, TRW. It has no statistical relationship with pay more money. The opponent cannot understand the original message. Clear? This is a Hill cipher mechanism. Okay. And the next mechanism is, or the next substitution technique is polyalphabetic cipher. It is something like a monoalphabetic cipher, but a set of related monoalphabetic substitution rules are used. Here key determines the particular he determines which particular rule is chosen for the given transformation. And one of the best known and the simplest polyalphabetic cipher is Vigneret Cipher. Okay, here we can use a set of related monoalphabetic substitution rules consist of 26 Caesar ciphers with shifts from 0 to 25. Also, we can use a Vigneret table here for the substitution. So, polyalphabetic cipher, it is a substitution mechanism in which number of monoalphabetic ciphers are, or substitution mechanisms are used. One of the simplest polyalphabetic cipher is Vigneret cipher, in which Caesar cipher mechanism is used for every alphabet. Clear? So we can use a 26 Caesar ciphers because the English alphabet contains 26 letters, right? So we can use the 26 ciphers all together to form a polyalphabetic cipher. That is a Vigneret cipher, and in which Vigneret table is used. What do you mean by a Vigneret table? And this is the structure of Vigneret table. Okay. In which we have a table plain text versus key. That is, if we are using the plain text A with the key A, that is at the left side, you can see A versus A, and the output is capital A. So, A plain text is encrypted by using small a key. What we get? Capital A is get. We can use A as plain text, small a as plain text, and the key as B. Then what we get as cipher text? Capital B is the cipher text. Likewise, we can use this Vigneret table for encryption mechanism in polyalphabetic cipher. Clear? Vigneret cipher is a polyalphabetic cipher in which Vigneret table is used. Here we can choose a key for encrypting the plain text into cipher text. Consider the example here. We have the plain text. We are discovered, save yourself. This is the plain text we have to encrypt. And the key is used as deceptive, word deceptive. Clear? So in polyalphabetic cipher, we are using the key as long as that of the message or the plain text. So we have a plain text, we are discovered, save yourself. So the key is deceptive. So we have to take it as long as that of the plain text. So we can use deceptive. Again, multiply that. Deceptive, deceptive, deceptive. For ensuring its length is same as that of the plain text. Clear? You can see in figure the key length of the key and the length of the plain text is same. First figure. Okay. Then by using the table that we had already discussed, that is Vigneret table. By using that table we can convert, or we can choose the monoalphabetic rules for each key and plain text pair to convert it into cipher text. First letter of the plain text is W. Okay, and the first letter of the key is D. By using W and small d, we get set as the cipher text from the Vigneret table. Clear? This is the first mechanism of the polyalphabetic cipher. And in the second figure, you can see we have the plain text same as that of the previous one. That is, we are discovered, save yourself. And the key is deceptive, the word deceptive. In first figure, we are repeating that words for making the length of the key is same as that of the plain text. But in the second case, you can see that after deceptive, we are using some of the first part of the plain text to make the key length same as that of the plain text. So after deceptive, we are using we are discovered SAV. Right, that is the first part of the or some part of the plain text for making the key length same as that of the plain text. Clear? This is the second mechanism for polyalphabetic cipher. So by using the Vigneret table, we can again convert this plain text into cipher text. Then you can see the cipher text that is in the first figure and the cipher text that is in the second figure is different. So key determines the cipher text. If you are using one type of key, then we get a cipher text. If you are using another type of key, we can get another cipher text. Okay, that is actually the benefit of this polyalphabetic cipher. Clear? And the third mechanism, that is one-time pad. It is actually an improvement to the Vigneret cipher. Vigneret cipher is a polyalphabetic cipher. Here also we are using a random key as long as that of the message, and the key cannot be repeated here. The key is used to encrypt and decrypt a single message and then discard it. That is, for every plain text letters every plain text we are using a unique key. After that they are discarded. Okay. So each new message requires a new key of the same length as the new message, and such a scheme is known as one-time pad. It is unbreakable and it produces random output that bears no statistical relationship to the plain text. And the cipher text contains no information whatsoever about the plain text, and there is simply no way to break the code. So one-time pad is a substitution cipher technique, and it is an improvement to the Vigneret cipher. It's also a polyalphabetic cipher. Here also the key length and the plain text length is same, but we are using a random key to produce a random cipher text. That means if we are using one key for the one plain text and for another plain text we are using another key. That is a unique key for each plain text is used in the case of one-time pad. Okay, so it's very difficult to break the code. It is somewhat unbreakable. Okay, and it produces the ciphertext. They have no statistical relationship with the plain text. Clear? So these are all about the substitution techniques. We had already discussed the Caesar cipher, monoalphabetic cipher, playface cipher. In this video, we can see Hill cipher, polyalphabetic cipher, and one-time pad. You can see in figure, we have a ciphertext in first figure. Same ciphertext is used in the second figure also, but the key is different. Then we get different plain text. Okay. And the next mechanism for the next cryptographic method is the transposition technique. Actually, substitution techniques is the replacement of one plain text letter by another letter. That is actually substitution. Replacement is there. But in the case of transposition technique, we are using some permutation mechanism. Actually, what is permutation mechanism? It is something like a rearranging of letters. Okay. So here some sort of permutation is performing. So first technique is rail fence technique. Here we have to encipher the message, meet me after the toga party. That is the plain text message. What we are doing is that we are taking two letters at a time and write down a sequence of diagonals. Okay. We have to encipher the message, that is meet me after toga party. That is the original message or the plain text that we have to encipher or encrypt. In rail fence of depth 2, we are taking two letters at a time. Why we are using two letters at a time? We are using a rail fence technique with depth 2. Okay, that is why we are taking two letters at a time. So two letters at a time means first we are taking ME as one pair. Next we are taking ET as next pair. And the third one, ME is third pair. Then AF, then TR, then TH, then ET, OG, AP, AR, then TY. These are the pairs. Clear? Then take these pairs, then write down as a sequence of diagonals. They are written as in a diagonal form. Clear? You can see in figure like this. ME written as in diagonal form. Then next pair AT also in diagonal form. Then ME diagonal, AF diagonal, TE diagonal, like that. So you have to encipher a particular message. Choose the depth of the rail fence technique. Take that pairs. Then write down as a sequence of diagonals. Then after return, you have to read in a row-wise manner. That means the encrypted message is like this. First row is ME, MA, TR, HT, GPRY. Then the second row ETE, FET, EO, AAT. Okay. So this encrypted message or the ciphertext has no relationship with the original message. Clear? This is the rail fence technique. It's a transposition technique. And the next mechanism, it is more complex than that of the first one. Write the message in a rectangle form. We have a plain text message. we take the message and write down that message in a rectangle or row by row form. Then read the message in a column wise. First, we have to choose the key. Key is the order of permutation. Clear? So we have a plain text, attack postponed until 2 XY. That is the plain text that we have to encipher. What will happen is, first we choose the order of permutation. That is the key. Key is 4312567. Okay, this is the order of permutation. Clear? And the plain text is constructed like a matrix or a 6 by 4 matrix. Row by row, we can write down the letters of the plain text. Then next stage, we can read column wise. Okay, so first column, key 1, TTNA. Then second order, APTM. Third order, TSU. Like that, up to we can write the column 7. Is it clear? That means first we have to choose a key. It is the permutation order or column order. Clear? Then plain text letters can be arranged row by row. Then read that row by row matrix in a column wise manner by using the permutation order. That is the ciphertext. Clear? Same way, we can increase the strength of this transposition techniques by using a double transposition. First, we are converting the original plain text by using the key to a ciphertext. Again, we can take the ciphertext. In second figure, you can see input as the ciphertext of the first figure. Okay, we can take that input. Again, we are performing some transposition to produce another ciphertext. So it is a double transposition techniques. Clear? So cryptographic method, there are of two types, substitution techniques as well as transposition techniques. Next, we can study what you mean by a Rotor machine. Actually, this Rotor machine is a multi-stage encryption mechanism. It is more difficult to cryptanalysis, or it is more difficult to break the code. Okay, and this machine, this Rotor machine consists of a number of independently rotating cylinders through which electrical pulses can flow. So rotor mechanism or rotor machine is a multi-stage encryption algorithm in which a number of rotating cylinders can be used. Through these cylinders, electrical pulses can flow. For each cylinder, we have 26 input as well as 26 output pins. And each input pin is connected to output pin by using the internal wiring mechanism. Okay, this is the general introduction of a rotor machine. It is a multi-stage encryption scheme. Here, number of rotating cylinders are used, and each cylinder with a 26 input pin as well as 26 output pin, and they are connected by using internal wiring mechanism. And this is the structure of rotor machine. Here 3 cylinders are used for our convenience. So each cylinder have 26 input pin as well as 26 output pin. In the first cylinder, you can see 26 pins are arranged from A to Z. alphabets A to Z. That is, each input and output pin with a letter of alphabet. Then a single cylinder defines one monoalphabetic substitution. So if an operator depresses a key for the letter A, an electrical signal is applied to the first pin of this first cylinder and flows through the internal connection to 25th output pin, and machine with a single cylinder. After each input key is depressed, the cylinder rotates one position so that the internal connections are shifted accordingly. After 26 letters of the plain text, and cylinder would be back to normal position or the initial position. Okay. So in the first figure, you can see fast rotor cylinder. Input pins are assigned the alphabets A to Z. If we are pressing the A pin, that is the 24th pin of the fast rotor, and it is connected to 24th pin output pin. Then in the next medium rotor, this 24th pin output of the first rotor is connected to the second rotor 24th pin. Then from 24th pin to 24th out of the second rotor. Then 24th output pin of the second rotor to 18th input pin of the third rotor. Then it will connected to 18th output pin of the third rotor. It will produce B as output. So if we are pressing capital A in the first rotor, if it is a 3-cylinder mechanism, it will produce B as output. Clear? We are using a 3-cylinder mechanism. First figure, A figure, initial setting. So we are using 3-cylinder mechanism. Each cylinder has its own 26 input pin as well as 26 output pins. Clear? And they are internally connected. All the cylinders are internally connected. That means output pin of the first cylinder is connected with input pin of the second cylinder, and the output pin of the second cylinder is connected to input pin of the third cylinder. Likewise. Okay. So if we are pressing capital A, that is the 24th pin of the first cylinder, and it is connected to output 24th pin of the first cylinder. Okay. From this second cylinder, that is 24 to 24, then 18 to 18. So we are producing B as the ciphertext for the capital A as the plain text. Okay, for corresponding A, plain text letter A, we are getting B as the ciphertext by using a rotor machine. Clear? And if we depresses a key, it will rotate. The cylinder rotates, or the internal connections are shifted accordingly. After 26 letters of the plain text, and the cylinder would be back to the initial position. Clear? This is a rotor machine scheme. And the power of this rotor machine is to use a multiple cylinders. If we are using a single cylinder, it is somewhat simpler. But if we are using number of cylinders, then the power of the rotor machine is somewhat high. And the next mechanism is steganography. What do you mean by steganography, and what is the difference between the cryptography and the steganography? Actually, the cryptography, we are converting something to something. Okay. But in the case of steganography, we are hiding the message or conceal the message. That is the main difference. Clear? In cryptography, we are converting the original message into a different message. But in the case of steganography, we are not converting the original message or the plain text into some other form, but we are taking the original message and hide some part of the message. Clear? That is actually steganography. Actually, the methods of cryptography render the message unintelligible to outsiders by various transformation of the text, but the steganography conceal the existence of message or hide the existence of message. And there are 4 types of steganographic mechanism. One is character marking. What do you mean by character marking? We are using some pencils for overwriting the selected letters or printed or typewritten written text. We are using some pencil mechanism and we are overwrite some part of the plain text messages or some selected letters of the plain text message. And these marks, pencil marking is not ordinarily not visible to users unless the paper is held at an angle to bright light. Okay, that is character marking. And next case is invisible ink. We can use some invisible inks to write the original message. It is not visible to users until we are using some heat or some chemical is applied to that paper. They are visible only after applying some heat or some chemical. That is the second mechanism, invisible ink. Clear? So mainly steganography is the concealing of the message or hiding the message. There are 4 types. One is character marking. That means we are using some pencils to mark some letters in the plain text. They are not visible to normal eyes, but if we are applying some light on the paper or on the plain text letter, we can visible that characters marked. Okay. And the second mechanism is invisible ink. We are using some invisible ink to hide the plain text letters. If we are applying some heat or chemical, then we can see that original message. And the third mechanism, we can use pin punctures. Small pin punctures are on selected letters are not ordinarily visible to the normal eyes unless the paper is held up in front of the light. Also, we can use a typewriter correction ribbon. That is, these ribbons are used in between the lines. It's a black ribbon, and the result of the typing with the correction tape are visible only under a strong light. So all these mechanisms are used for concealing the message, but we can apply some heat or some chemicals or some bright light for making visible. Okay, these are the steganographic mechanisms. So already we had discussed what you meant by computer security, network security, what are the OSI architecture concepts or aspects. There are 3: security, attack, service and mechanism. Next, we had studied the introduction of cryptographic mechanism and the 2 cryptographic methods, substitution and transposition techniques. After that, we had studied rotor machine and steganography. Okay, thank you.